All right, good morning. Let's see what we got here, attendance wise. All right, so we have in person 1, 2, 3, 4, 5. We got them all in person 1, 2, 3, 4, and 5. Let's look out in the land of homeward bound people. We got Amara, yes, good. Beckley, still no Beckley. Nakaya, nope. All right then. Childs? No child.
Here. I'm here.
Duncan, Lauren, Duncan, yes, good. Emily. No, Emily. Oh, okay. Childs, you are here. All right, cool.
I just got here too.
No, Emily. Josh, we got Josh. Omar, we got Omar. Tori, down at the bottom. Tori. Tori, no Tori. Hannah, so Hannah. Bella. Bella goes by something different, but I don't see either of those. Bella, you out there? Namara is here. Micah is here. Nick is here. Sanchez is here. Mukuli is here. And Lucille is here. Oh, Jay is now. Yeah, Bella's back. All right, cool. Boom, boom, boom. All right, cool. Let's take a look at what we've got for today. Visualizer. We've got some problems that you guys did on solutions yesterday. We want to take a look at those first. And then we will take a look at the laboratory for tomorrow. It has been mentioned that this is the first laboratory that students will perform this semester. All the rest have been recorded up to this point. Is that true? And you did the other thing at home, building the model. Yeah. Okay, good. So this will be fun. They're going to be working with a hot plate, some measuring devices, and what we call a solution. A solution has a solid dissolved in a solvent. So we've got that going. Now, this past evening, you were asked to do problems 1 through 4 using the different setups that I've taught you. Basically, here we are looking for molarity. Molarity is moles over liters. So moles over liters. We need something from the reading that will give us moles. What from the reading can we get moles from? What about the sodium chloride? All right, so we have 2.6 moles, Henry says. How can we get from moles to moles? We don't have to. So that's perfect. That's exactly what we wanted up top. So we're good. And what up there can we get liters from?
2.1.
2.1 liters. Well, we wanted liters, we got liters. We're done. All we got to do is take 2.6 divided by 2.1, and we got it. That is 1.2. 2 significant digits here. 2 significant digits here. So we're good. 1.2 moles per liter. We could have also written this, if you wanted to, as 1.2 uppercase M. 1.2 uppercase M. Any other questions on that? Little easier. Maybe you, whenever you first saw it, you thought that was going to be a hard one, but that one is definitely a pretty easy one. Pretty easy one. All right, let's try the next one. We got 0.75 moles, and we have 225 milliliters of solution. We again want the molarity, so molarity is moles over liters. What can get us moles?
0.75.
Yeah, right? 0.75 moles. What can get us milliliter? Yeah, so you could convert this in your head to 0.225 liters if you wanted to. There's no need, because by now you should know there are 1,000 milliliters in 1 liter. We know the 1,000 goes on top because we want the milliliters to cancel out. Then we have moles over liters. 0.75 times 1,000 divided by 225. We get 3.33. How many significant digits will our final answer have? Based on what? How many significant digits do you think the moles has? 2. Which one of these is not significant? The 0, right? So we're going to have 2 significant digits there. It's going to be 3.3. Some of you guys don't even put the 0 on stuff, right? You just put 0.75. So it's not a significant 0. To be a significant 0, it has to be between 2 significant digits, or it has to be, yes. Or if it was 0.750, the 0 is to the end of terminating and to the right of the decimal. All right, so 3.3 moles per liter. Next, a chemist prepares a 4.0 moles per liter aqueous solution with 36 grams of calcium nitrate and water. What is the molarity? So again, we want moles per liter. What are we going to use to get moles per liter from this? We've got to convert 36.0 grams to moles. Okay. So we're going to take 36.0 grams and put that on top. Oops, 36.0, not 3.60. And we have 4 liters on bottom, 4.0 liters on bottom. So we saw here, we didn't have to change anything. Here we saw we had to change milliliters to liters. Now here we've got to change grams to moles. In order to change grams to moles, every 1 mole is 164.1 grams. So if it's on top, we multiply. If it's on bottom, we divide. 36 divided by 4 divided by 164.1.
The answer is about 0.05484.
How many significant digits should we have? 2. So we end up getting 0.055 moles per liter. 0.055 moles per liter. Questions there? This 0 right here is not significant, right? All right, you dissolve 10 grams of manganese chloride. 10 grams of manganese chloride. We want, again, moles per liter because we want molarity. We got to get that grams to moles, and we have 100 milliliters of solution. Again, you could change that to 0.1 in your head. But again, I just think it's easier to do everything using the dimensional analysis. Every 1,000 milliliters is a liter. And for this substance, every 125.8 grams is a mole. Again, I know what goes where because the units have to cancel out. We've been saying that since August of last year. If it's on top, we multiply. If it's on bottom, we divide. 10 divided by 100 times 1,000 divided by 125.8.
The answer is about 0.7949.
How many significant digits for our final answer here? 3. 0.795 moles per liter. Again, you could have wrote this as 0.795 moles with the big M. Questions there? We had 10.0, which is 3, and we had 1,000.0, which is 4. So we went with the 10.0, which is a smaller number. All right. For this evening, don't forget that you should be turning in a solubility graph, right? I'd also like for you to try these two problems right here. So we're going to do 5, and then we're going to assign 6 and 7 for tonight. Basically, you know how hopefully to find molarity, but sometimes the molarity is used within the problem. I'm going to show you again how we can find how to use that molarity in the problem. So we have 2.1 liters. Let's see if I can make that a little bit better looking. Better. You have 2.1 liters of aqueous 0.33 molar sucrose solution. How many moles of sucrose does the solution contain? This is similar to the laboratory you're going to do tomorrow. Those of you at home will be following one of the people in the laboratory. They will have a certain volume of solution. They will need to find the molarity of that solution. In order to find the molarity of a solution, you need to know the number of moles, right? They're going to find the moles experimentally. Let's show us how we can find the moles mathematically. How many units does moles have? Nope. Unit. 1 or 2? 1, right? If you still don't get that, look at this. This is liters. That's 1 unit. This is moles per liter. That's 2 units. This is 1 unit. So I want to start this whole thing off with the 1 unit thing, 2.1 liters. Oops, 2.1 liters. Good. Now, that means that liters has to go where in the next step? On the bottom. If only there was a way I could get from liters to moles. Well, believe it or not, 0.33 molar means that there are 0.33 moles for every 1 liter, or it means that 1 liter is equal to 0.33 moles. I could really use either one of these. They mean the same thing. In this particular case, though, I have liters, so I want to use this one right here. Every 1 liter is 0.33 moles. Imagine if I started with moles, though, then I would want to use this one right here, because then moles would cancel out and I could get liters. 3.1 times 0.33. How many significant digits will this have? 2, so 0.69 moles. Now watch this. 0.69 moles. Well, every 0.33 moles is 1 liter. 0.69 divided by 0.33. There's our 2.1, right? We could use this to go from liters to moles, or we could use it to go from moles to liters. That's the beauty about it all. It all comes together, and the faster you see this, the easier this class will be for you, like 100-fold. So again, I'd like for you to do 6 and 7. We also want to take a look at the laboratory. So I know Canvas has been a little bit shady today. So let's take a look here. You guys will want to make sure that you get onto your computers because you're going to talk to the lab groups from home. And you're gonna wanna go ahead and join the Canvas, just, I'm sorry, the Zoom, just make sure you're mute. What I'm gonna do is I'm gonna go ahead and print these guys out, a copy of the laboratory. So I need one, is there anybody behind you? No, 1, 2, 3, 4, 5. I need 6. That's just gonna take about 40 seconds, which is gonna give them enough time to get on the Canvas for you guys. Anybody come in late, Emily or whoever else was absent on there? Can't remember. Doesn't look like it. All right, I'll be right back. Hard copy. Yep. There you go. You probably want a hard copy for the laboratory to tell you. That work water or what? Am I thinking it's Monday? All right, so the laboratory is pretty straightforward, but you can see that we don't have a procedure. That's what they're going to work on with you in a few seconds. They're going to need your help from home because this is one of the hardest things they'll probably do this week, is to sit here and work in a laboratory for the first one this semester while you're watching them. They're going to need your support and your help and your guidance from home. So please make sure that you do communicate with them, even more so than you communicate with me. Otherwise, they may just end up turning off the camera and then you'll have to watch another boring video of me do it. So keep that in mind. All right, so let's take a look. You want to find the molarity of a sodium chloride salt solution given by your teacher. So each student will get a different solution. Each in-person student will have other virtual students with them. We will do this tomorrow. So the plan is that you have a procedure written near the end of this period. So we are going to change it up a little bit. I'm not worried about the percent mass this go round, and I'm not worried about the molality. So all we are going to find is the molarity. I'm going to flip this over for some key notes. What do you need to find molarity? Moles in the liters. So if you are handed a sample of solution, how can you find the liters? Measure it. So students need 30 to 40 milliliters of solution. Now notice I say 30 to 40 milliliters of solution. That means they'll go up there and they'll grab about 30 to 40 milliliters of it. Then they will go back and measure the particular amount. They need to know the exact amount of it. And that means we're using a graduated cylinder. And I'll show you a graduated cylinder in a few seconds. How do you spell cylinder? So I'll show you how that works. Has everybody in here used the graduated cylinder before? Graduated cylinder is the big long one like this. This measures volume. A beaker is this guy. This does not measure volume. This estimates volume, but that's not a measurement. We're dealing with significant digits here. If you have a beaker as your volume measurement, that's going to cost you a lot of that accuracy. So why is it important that we have this number 30 to 40? That way they can go up there with the beaker, they can quickly get 30 to 40, and they don't spend all their time back there. Is what's going to take the longest time for this is to separate the liquid from the salt. And how do you suggest we separate the liquid from the salt? The homogeneous mixture. Because what's the other thing we need? We need a volume and we need moles of salt. So how are we going to get the moles of salt of this? Heat it up. What's going to happen to all the water? Right? So for your procedure, you need to know the volume, the exact volume of the solution. And then once you know that, you're going to vaporize the water. Right? Now there is a problem here. We're going to, you can't put this on heat. Cannot be heated. Guess what? This can be heated. So once you get the known measurement of the volume, you're going to dump it into a beaker because we can place a beaker on a what? Hot plate. Yep. Right? Now there is a little problem here. For this beaker on the hot plate, use the big beaker, and I'll tell you why in a second. Big. How's the salt going to look when we get done vaporizing all the water off? Is it going to be nice and fresh, and we're going to be able to pour it like a sprinkle salt on French fries? It'll be wet until we completely dry it, and as we completely dry it, it's going to stick to the side of the beaker. There's no way we're going to be able to pour this onto the scale. So how can we get the mass of the salt if it's all stuck to the beaker? You got it. So there's a little side step here. Before we do this, vaporize the water, we got to know the mass of the empty dry beaker. Right? Because the mass of the salt and beaker minus the mass of the beaker equals the mass of the salt. Pretty, right? We got to know the mass of the dry beaker. Does that make sense to everybody? Right? You want to find your dog's weight and they won't sit on the scale, and you know your weight, grab the dog, get on the scale, and then subtract your weight from the total weight, right? Boom, boom. Same thing. All right. So if we take a look at that, that data will give us grams of sodium chloride, which is the salt we're using, Well, we should know the milliliters from the graduated cylinder. We can change grams into what? Moles. And we can change milliliters into liters. And that will get us molarity. That's the basic things we want to do. All right, let me show you this before I make these breakout rooms. Let me show you the equipment we're using. This is our standard hot plate. On here, it has two knobs. All you care about is the heat knob. Probably want to get this all the way up after you do it. These are our standard beakers. This is our graduated cylinder. So everything you need to use is going to need to start clean and dry, right? The way you dry a graduated cylinder is a little bit difficult. You take a glass stir rod, which is basically just a piece of glass. You take a napkin. And you roll the glass stir rod on it. Once you do that, you got a hold of the napkin and you can stick that into there and get all of that moisture that's down at the bottom there. And then it's dry. You can sit that in the middle of the table so it doesn't roll off or a partner doesn't knock it off. Now this guy's ready to go. You'll probably want a 100 milliliter beaker ready because you can pour that up to 40. And then you know you have at least 40 milliliters of the solution. Then you can pour that into here, the graduated cylinder, and get the actual reading between 30 and 40, right? This is just an estimate. You never actually get a volume from this. This just tells you if I'm going to go over to the lab table and grab some chemical, I want about 40 of it. I'm going to pour this up to 40. This will give me the actual volume, and that's very important. Once I get the actual volume out of these beakers, I want the biggest beaker. Why? Yeah, right? There we go. So we're going to use the 400 milliliter beaker. Inspect the bottom for cracks, because if I heat this and it cracks, then it's going to pour all over, and then I'm going to have to restart this experiment. Some people don't check those things. This needs to be clean and dry as well. And what else do we need to know about this guy? We need to know the mass of this guy. Then we're going to pour our solution on there, swirl it around, and put it on the hot plate. With the hot plate cranked up as high as it can go, this will start boiling. And here's a big thing, is I need to be prepared. As soon as this gets down really, really low, if I don't pull it off of the hot plate right when I see that precipitate forming, that salt forming, I'm going to have a bad time. And I'm going to let it sit here and chill a little bit, and then I'm going to turn this down to about 200. Or if you're on a 10, maybe to 3. If you have one that goes from like 1, 2, 3, 4 up to 10, then maybe to 3. Now the reason for that is that salt will form, and that salt will form and trap water molecules. Well, as those water molecules expand, what do they want to do? Poof, right? You may have had this happen in the microwave to you. What does that mean is going to happen to some of the salt in there if those water molecules expand too fast? Yeah, they're going to fly out. But whenever I go to get the mass of the salt in the beaker, that means my mass is going to end up being lower than it should be, right? So as soon as you sit there and see those particles start forming, or you hear crackling, you know you got to put this off to the side. Let it sit off to the side, let this cool down a little bit, and then put it back on. If you hear the crackling again, take it back off. Put it back on, take it back off. You're not done until you can see that all of the water is gone. And when water vaporizes, it will recondense on the edges here. If it recondenses on the edges here, it will eventually vaporize off of those edges. That's what you want in your final product. Then after that's done, after you sit there and you see that all of it's gone, or maybe if there's just like one bubble here, and you know that by the time this whole thing is cooled, that it will be gone, take and let this sit until you can touch the bottom. And don't try to touch the bottom immediately. You won't be able to do it. Give it, 4 minutes or something like that until you can touch the bottom. And when you can touch the bottom, you can handle the glass itself with relative ease. Only then will you take the weight a second time. Why is this? Well, there's several factors. A major factor is that this is made of metal. If you set some hot glass on metal, we know that metal absorbs heat very quickly. What could happen to the glass? Shatter. That's no good for anybody. Your experiment's done. You don't have any results. The other thing is the bottom of this is made of hot glue. If you put hot glue on there, what's that going to do to the glue? Melt it, and then that's going to break this thing. If this is too hot when you put it on there, it can destroy this. So we need to make sure that we keep those things in mind. You should not get the mass of something unless you can touch the bottom of it with your hand. All right, so that's what I've got. I'm going to open up 5 breakout rooms.
Are we doing this tomorrow?
Yes.
Because I won't be here tomorrow.
All right, I'm going to open up 4 breakout rooms. Everybody else good? I'm going to open up 4 breakout rooms, and then you guys will talk with your groups, and hopefully you guys can come up with a decent procedure, like a step 1, do this, step 2, do that type of procedure. I'm going to let you choose, but if the breakout rooms don't look evenly spread out, I'm going to move some people. So there we go. So that means we'll have to record one of you, and then Henry can watch it. Right? All right, let me open up the rooms, and I'll see you guys later. What? You're not going to be here.
I'm gonna be in Georgia like tomorrow.
Cheating the system. It sounds like your parents don't respect the public educational system. You should also join somebody else, because you're gonna have to do it.
Mr. Jackson, I can't join
Video,
any of them.
whatever, but yeah.
Or you're not even there.
Just to make
I
sure you guys
can't.
understand, I don't put you in breakout rooms. I actually let you choose them.
Yeah, like it's
Tony's
not
ready
letting me.
for people to join him. Christian's ready for people to join him. Just waiting.
Mr. Jackson,
for others.
can you hear me?
I don't think you
that?
can hear us.
That's what I think, but I can't join
You're
any
not
of
even gonna be
them.
here.
Hey, Mr. Jackson, we're talking.
Yeah, what do you need?
Oh, I thought you couldn't hear us. Sorry. I was just saying that I can't join any of them. Like I'm clicking join and it won't let me.
All right, give me 1 second. Let me make sure that this is right. I'm gonna
Okay.
in the breakout rooms. How did Tony and people get in then? How's that? Oh, weird. Maybe whenever I grab the computer, I press something. Is that good?
I still can't join. I don't know why.
What?
I don't know if it's just me.
Let me try something real quick here. Breakout rooms. Have you updated to the new thing or no?
Yeah, like I did it last time. I don't know why this time it won't let me.
It worked for a minute just now, but you pressed something else.
Okay. I think it's just tomorrow then.
It won't let me either.
Yeah, give me 1
The,
second.
the whole breakout rooms are gone now.
I'm gonna end them and then we're gonna recreate them. And then we'll try again. Who are you talking to? Okay. Join this one again. If you guys leave the breakout rooms, it happens quicker. Or we have to wait 12 seconds. Tony, you're still in. You're slowing us down. All right. Let's try again. So breakout rooms, recreate, let participants choose the room. There are 4 of them. Recreate them. Open all the rooms. Try now. Tomorrow, I'm just gonna put you in one. Unless you can join.
I'm trying right now.
Who's that? What's your last name? Batavia, right? All right, I'm gonna put you in room 1. So you may not have the most up-to-date. Tomorrow, I'm gonna put you in group 1. And I'm gonna just grab people and start putting them into room 1, 2, or 3, because I'm assuming that you guys are having trouble. There we go. So go ahead and move to those breakout rooms and then we should be good. Henry, what's wrong with you? There we go. What's that? You're not gonna be here either? Okay. Yeah, if you're not gonna be here, you need to tell me, otherwise these people are gonna be like, feel left out, you know? Cool. A what? That's a selfish response. That I care about me problem. Sounds like that's gonna be a bigger problem than them just missing out on the lab for the rest of your life.
All right, guys, gameplay. So first we acquired the weight of the okay? And after we acquire the weight of the feature, then we're gonna acquire 30 to 40 milliliters of the solution. And then after we find that, well, after we acquire the solution in the beaker, we're gonna walk over to our station and then get an exact measurement of the graduated cylinder. And then after we write down our exact measurement, we're gonna put it back in the beaker and then turn the
What's that?
top plate on all the way, and then we're gonna put the beaker.
Can I, give me 1 second.
And then we're gonna wait for all the water to boil. And then after we only have salt, we're gonna let the beaker cool off. And then we're gonna subtract the beaker weight from the weight of the beaker with the salt.
And then just move down that step that we just had and just make that the second one.
I can't do that because it's still live. I can't do that.
Step 4 is
Yeah, but you have that written down.
Would
on
that
the back
be-
of this, don't you? Yeah.
putting the measured solution back into the beaker and putting it on the hot tray.
Yeah, and then putting it on the hot tray.
Did you just listen to Henry?
Yeah.
Solution into large beaker.
No one asked any questions, so.
Did they write that down?
Did you guys write all of that down?
So that when Seth sleeps tonight, he doesn't have to remember all that? He'll be ready to go whenever he's in the laboratory tomorrow.
Take your microphone
Without
off
losing
mute and
any
put it
salt.
back on mute if you wrote that down.
All right, and then next we'll, after all the water's evaporated, we'll take the mass of the beaker and the salt.
That's the state of affairs that we're at, Henry. Take your microphone off mute and put it
Well,
back
they're
on
not
mute.
gonna talk, so.
Yeah. It's really stunted people's society thing, right?
Do what?
What's
Social
done in
behaviors are
society?
different now, right?
Yeah.
Yeah, we're soft.
You feel like you're becoming softer?
Yes.
Not gonna lie, did a good job on working.
Take the mass of the beaker and salt.
Wait, can I just turn this in as a physical copy?
No.
Oh, man.
Remember that
Subtract from.
any physical copies anymore.
Dang. Bro. Yeah. You're my bro teacher.
And then after we know how much salt we have, we will divide the. We will convert the grams of salt into moles. Now, I don't know how to do the math. Someone at home's gonna have to do the math. Just FYI.
All right, I can do that one.
All right, right on. Salt into moles and divide by milliliters times 1,000. Okay, and then we'll have the molarity.
Do we like assign tasks to group members, or do we have to all do it ourselves?
You want to turn one in?
Well,
Like one single one in? Is that what you're saying?
what I'm saying is like,
Yeah, you should be able to task them to do stuff. Because they're part of your group, right? If they were
You
in the
guys-
laboratory, then you would sit there and say, hey, clean this out.
Do you guys have the lab sheet or like on your computers?
We should have it on our computer.
Yeah, we have to calculate the percent error too, but that's it. We'll be done after that. It shouldn't take too long tomorrow.
Yeah.
Yeah, and also someone at home should write down the measurements that I give you guys, so like we all have a consensus.
Send them away then.
Yeah, we're done for today. See y'all tomorrow.
Josh, you got any questions before we close this out?
No, I'm good. Thank you.